All right, everybody, let's go ahead and work on solving polynomials. This is section 5-3 in the textbook, and this is a section, man, it brings so many different things together. I want to check out some things with you. First, I want to remind you that polynomial functions, they could be linear, quadratic, cubic, they could be any of those things, and polynomial functions can be graphed. So if we start off just establishing the fact that if you can graph a polynomial function, then you can solve a polynomial function. Because let's remember that zeros are the solutions to a polynomial function. They look like the points, the zeros, they look like the points on the x-axis where our graph touches the x-axis. So if a graph has different end behaviors and so on, all we're really trying to do is identify where that curvy line, or sometimes straight line, touches the x-axis. So then you might ask, why don't we just graph everything? Well, we don't because of imaginary numbers. We also don't want to graph everything because it's kind of a cumbersome way to solve a problem. So let's go ahead and recall one thing before we move on to this review piece. Recall that if you have one imaginary root, you're always going to really have two, because you're always going to have a positive and negative I. So a couple of things that we're going to strategize on. Yes, graphing is a good way to solve, right? You can graph any polynomial, look for the zeros, and that will give you the real solutions. That will not give you the imaginary solution. So graphing won't always give us everything that we need. A couple other things that we can use, right? A lot of these are going to be review. I'm really only going to touch on the new stuff. A reminder, yes, you can use the quadratic formula, but you can only use quadratic formula for stuff that's quadratic. That means to the second degree. So yes, quadratic formula, it's fantastic. We still love it, or at least I do, but its use is limited to quadratic stuff only. Now, factoring. There is an extensive kind of page 297 that you may want to consider pausing the video and looking at. Page 297 has a whole list of strategies on factoring. The only thing I really want to point out here is, unlike graphing, where you have a y equals or an f of x equals and then your polynomial, we're going to change out the f of x and we're going to put a zero in its place. So when we're solving by factoring, we're really trying to use that zero product property. So we need our polynomial to equal zero. So all of the ones I have here are going to equal zero. Most of these are going to be review only, so I'm going to zoom in a little bit. The first one, the greatest common factor. Right, let's imagine you have x squared plus 2x equals 0. You can factor out a common factor of x, and then you have x equals 0, or x is -1, right? Because those are the values that would make those two individual statements, this one and this one. If either one of those is 0, the whole thing is 0. So 0 and -1 would be our solutions. You'd write x is 0 and -1, and that would be your solution. For quadratic trinomials, this is just good old-fashioned factoring. You could use the area model. You could use grouping if that's how your teacher taught it to you. That's not how I taught it to you. We use the area model. With that in mind, you would again have these two chunks. And if either one of them or both of them equals 0, then you have a solution. So x would be -3/2, or x would be 5, and those would be your two solutions, right? By the way, two solutions, highest degree is 2. So we're not missing anything. Same here, two solutions, highest degree is 2. So we haven't missed any imaginary solutions because we're getting them all listed. So we're in great shape so far. Now let's go down to perfect square trinomials. Now I have to admit, perfect square trinomials was one that I forgot regularly when I was a student. And I've honestly not really invested a lot of time into memorizing it as an adult. I'm good at, and so are you, factoring quadratic trinomials. These are just quadratic trinomials. So I just factor them like normal. I have to admit, anytime I see something that looks like a perfect square, I automatically assume, whether that's a good move or not, I automatically assume that the 3x and 3x make up 9x squared. And if I see a perfect square on the c value, I assume that 2 and 2 are going to go in there, and then I start experimenting. In this case, the signs have to be the same because when you multiply them, they give you positive. So, and the signs have to be negative because when you add them up, you need a negative. So boom, boom. They're both exactly the same. So 3x minus 2 is 0. So 3x is 2. And x will be 2/3. You might notice that this one is only one listed answer. And you have two things listed. That's because this one is a double. All right, so x equals 2/3 has a multiplicity of 2, and that gives us our two solutions, if that makes some sense. With that in mind, Difference of squares. Once again, difference of squares is one that I did recognize as a student, unlike perfect square trinomials that I have listed right here, that I sometimes had trouble identifying when I looked at them. Difference of squares was easy. There's always only two things. It's always subtraction. They're always perfect squares. So x squared is literally just x times x. 9 is 3 times 3. The signs have to be different because when you multiply them together, you get a negative. And you're going to get x is 3 and negative 3. One more time, both answers come out good. Now, what about these two, right? These are not difference of squares, but we can treat them like difference of squares. This is new. I'm going to put this in pink because this is something that you might not have known. I marked it off to the side because I wanted to pay special attention to this. In this problem, here's what I'm going to do. I'm going to go ahead and pretend that x squared is a perfect square, which it is, and I'm going to pretend that the negative 10 is a perfect square, and I'm going to break it down to its square root, right? Because the square root of 9 was 3 and 3, so the square root of 10 is the square root of 10 and the square root of 10, and now plus or minus equals 0, and then we could solve this, right? X is going to be negative square root of 10 or positive square root of 10, and once again, there are my answers. So while this doesn't feel like a difference of squares, we can treat it like one and it will still work. Same thing goes for if you have a perfect square at the back half, but not on the front half. We can go ahead and treat that the same way. Here's what we're going to do. The 16 will give us the 4 and 4. The minus will give us the plus and minus. The x squared will give us the x and x. And the 3 is the square root of 3 and the square root of 3. Now, the only thing that I'd probably do here is I wouldn't write them this way. I'd probably write them, I'll show you. I'd probably write the x first and the square root of 3 second so that the 3x doesn't look like it's both under the radical sign. So I'm going to erase here. It's not a math mistake. It's more of a writing piece of, I guess it's a way in which you could be thrown off a little bit. So that would be a way to solve this, right? And then just to show one example through, I'm not going to do them both because you'd have to do both. But if x roots of 3 plus 4 equals 0, you would just subtract x from both sides. Subtract 4 from both sides, divide both by the square root of 3, and you'd get x equals negative 4 over the square root of 3. Now, I know this isn't, what do they call it? It's not rationalized. We'd have to rationalize our denominator from here. That means you multiply both the top and the bottom by whatever the denominator is. And we're going to get negative 4 roots of 3 over 3. And then you could imagine, again, doing the same idea over here for the other one. You'd get your two answers. This is meant to be a review video, so I'm not giving instruction on. I'm simply reminding you of how to do it. And you would get your two answers. Now, with that in mind, let's keep on going down to the next piece. Factoring by grouping is another thing that was mentioned on that page 297. Factoring by grouping normally jumps out at me if I see 4 terms. If I see 4 terms, I tend to look at the first 2 and the last 2 as pairs, and I look for GCFs. And I hope I find one. Now, sometimes you find them, sometimes you don't. But if you get lucky and you find them, like in this first pair, x squared is the greatest common factor. So x plus 1 is the remainder. Now what I'm really hoping I can do is I can find another GCF that will produce x plus 1. That's what I really want. Sorry, I have 1 in there. I should have 2. So I see the x, I see the 2. The only difference is that they're negatives, and these are both positives. So I can fix that by doing minus 1. All right, so now I'm going to take my x squared minus 1, my x plus 2, which occurred in both of them, and then I can solve from there. I might remind you that this thing in the beginning breaks down to x plus 1 and x minus 1. And then this one is x plus 2 equals 0. And you really should be able to solve it from there. You're going to get 3 solutions, negative 1, positive 1, and negative 2. And that, again, goes along with how many solutions you're supposed to have. We haven't even messed around with imaginaries yet. And I think we're about to kind of play around with that in our last piece. The sum or difference of cubes. Now, I really want to emphasize the fact that there are formulas that you can follow, and there's a lot of value in the formulas, but I'm a little worried that 5 years from now, heck, 3 months from now, you might forget what the formulas are. But what you might recall is that I see a cube, and that 8 is a perfect cube, right? 2x, 2x, and 2x are all examples of numbers that could be multiplied together to give you 8x cubed. And 1 is a perfect cube because 1 and 1 and 1 could all be multiplied together to give you 1. So what do I do with that? Well, what I see is that I got a 2x and I have a 1, but I'm not really sure what I'm supposed to do with that. So here's what I am going to do. I'm going to take 2x plus 1, and I'm going to use long division, right? That's why I have long division noted here. I'm going to take my 8x cubed. I need placeholders for the x squared and the x term, and there's my plus 1. And I'll probably fast forward the video, so I'm just going to work and get moving here. Smiley face at the end because I'm so happy it worked with no remainders. If we have remainders, then we're going to have to take it in a different direction. That is not what you're going to be facing in this section. So here's how we finish this off. We've taken the 8x to the third plus 1. I'm going to come down here below it, and we've decided that 2x plus 1 goes into it, 4x squared minus 2x plus 1 times. And now at this point, this part is easy enough to solve for 0. This part, we could do a variety of ways. We could factor it. We could use the quadratic formula. We could go ahead and solve it by, what are some other strategies? We could just use trinomial factoring, right? So there's a variety of different ways that we could solve that. The quadratic formula would work because it's quadratic, but you get the idea that you just then factor that next piece. So that is meant to be a review of the tasks you're going to need to do the work that's included in Schoology. I wish you good luck, and Zoom.